Well, hi, good morning, and thanks so much for joining me here in my shop while I try to go another step with this radio. At the last video, I kind of reached the conclusion that a couple of the shortwave bands were weak for some unknown reason. Whether that conclusion is absolutely correct or not, I'm still not quite sure. But I'm going to start hunting down what might be the cause of that. And I think really it's all about the front end of the radio, because if any signal reaches the intermediate stage, it's going to come out of the speaker. We know that because the AM or broadcast band produces pretty good signals and they come out the speaker quite nicely. The other bands don't seem to. So I think the problem has to be in the front end of the radio. So that's what we're going to focus on and check out, do some tests, and try to come up with a conclusion as to whether there's a problem. If I can nail it down to the component, that would be great. So I think really the first stage of this is a study of the schematic. I have two schematics here, but the area that we're going to be studying is absolutely identical on both of them. So I'm going to use the slightly better looking schematic with a little more information on it. I think the values of the components are put on it. So let's put it up here. Okay, so here we are looking at the schematic. This is a 2-pager. The second page has some layout stuff and the alignment instructions. So the part I really want to concentrate on is everything before this tube. So this is the mixer tube. It's taking what's coming in on the antenna and what's coming from the local oscillator, mixing them here, and then the output is being sent on to here. So what I said earlier is if a signal reaches this tube okay, it's going to come out the speaker. We know that because the broadcast band's working. For at least two of the shortwave bands, the output from the speaker is very, very, very low. You have to put a very strong signal on the antenna to make it here. The problem, I'm pretty sure, has got to be in this area. So that's the part I want to concentrate on, because that's the part we're going to be testing eventually. So let me zoom in on it here. So I'm usually speaking in these videos as if I'm talking to someone who has a fair bit of knowledge in radios. But I think I'm going to take it down a notch and explain this in a fair bit of detail. I have to warn anyone who watches my videos at any moment what I'm saying may not be true. I don't rehearse these things. I don't study up for them in particular. So I may say things that are generally wrong or specifically wrong. So put on your thinking cap while you're listening to me talk about this stuff. But probably the easiest way to go through this, I think, is to start with the local oscillator here, which is the part of a radio that people who don't know about radios wouldn't even know is in there. In fact, would be surprised to learn about. I think I mentioned this in the last video. When you're tuning a radio, you're really tuning the frequency of an oscillator. And the oscillator, just like a radio transmitter, is then the output of that is then used in this tube. It gets mixed with the antenna signal that's coming in this way. Coming in, let me just point out very carefully, coming in through this tube, getting a boost through here and meeting up with this local oscillator frequency here. And then something somewhat extraordinary happens in this tube. With the tube operating in a non-linear fashion, the tube will generate harmonics. In the harmonics will be components of the two frequencies that are put in. 4 components will come out. 2 go in, 4 come out. So one going in is the antenna signal you're trying to listen to. The other one is a signal produced down here by the oscillator. It's not really produced down here, but I can symbolically put it that way. Well, those two things get mixed together, and out of this tube, right on this wire here, this one, it says 226 volts. Out of this comes 4 signals. The original antenna signal, the oscillator signal, and then if you add those 2 frequencies together, the result is on this wire too. And if you subtract or find the difference between those 2 frequencies, that signal is also on this wire. The difference frequency, of course, is the lowest one. So you might be mixing two fairly high frequencies. Just as an example to make this clear. You might have a 10 kilohertz coming in here. You might adjust a local oscillator to, guess what, 10,455,000 kilohertz. Those two signals mix up in this tube. The difference between them, because I picked those numbers very carefully, is 455 kilohertz. If there's a 400, this is the main thing, if there's a 455 kilohertz RF signal on this piece of wire, it will find its way through the rest of the radio, because the rest of the radio is tuned to that frequency. The other components, the other three components, get thrown aside. They just don't make it through here. They can't make it through these tuned circuits. Well, they might make it a little ways, but they won't make it far. So in the end, you really have a radio here that receives one frequency in this part, 455 kilohertz. The radio can be designed and built very carefully for that frequency. This part, though, has to handle a wide range of frequencies, all the way from, in this radio, extremely low, 150 kilohertz, all the way up to 18 megahertz. That's a large range of frequencies. If you tried to make the whole radio amplify a large range of frequencies, you would have a lot of problems. But early radios were like that. They didn't use this frequency conversion technique and a fixed intermediate stage frequency technique. They didn't do that. They hadn't thought of it yet. So, okay, so that's roughly how the radio works. Mixes together two frequencies. The local oscillator, of course, is the one you're adjusting. So that 455 magic number, I don't know how to say this. It certainly gives you the impression that you're tuning across the band when you're doing it. So, and also, the capacitor in this radio has three sections. I should make this clear too, before I really get going on this. They're shown on this schematic nicely in this great big capacitor. You can spot them right away. And you can see capacitor number 1, section A, capacitor number 1, section B, capacitor number 1, section C. Back to the oscillator here. So if you were to look at this long enough, you would figure out that this capacitor is in parallel with one of these coils, whichever one has been selected by the position of the switch. This is the band switch here. In the schematic, they've shown this on the broadcast band. So pretty sure you can go long wave coil, broadcast band coil, or regular AM radios, we like to call it here, medium shortwave, and then the high shortwave. These two switches are connected together at the shaft, so when you can't rotate one without rotating the other, and this is true up here, here. So that's that multi-section big band switch. It's turning all these selectors, and mostly what it's doing, it's selecting one set of coils out of, or one coil out of a set. So what's the deal here? So the capacitor and the coil will resonate at a frequency 455 kilohertz above the frequency you're aiming for. I mean, they don't do that of their own accord. You're the one who's tuning them to that. And then the output is sent right to the grid of the detector tube. So the local oscillator frequency is sitting on this grid. Now, if we follow, this might just cause me a lot of problems. Let's go back here, follow it this way. So it's just, I just want to compare what's on the other grid to show you the antenna signal does get there. So the antenna signal is in this tube, coming out here very quickly, going through a selection of coils, in this case these coils, coming out. These coils are tuning against this capacitor, and the signal is sent there to a grid in the tube. So you have the local oscillator on this grid, and you have the antenna signal on this grid. And again, because of nonlinearities in the tube, they get mixed and you produce harmonics, and you get all those signals heading out. If you have a weak local oscillator, you get a weak signal coming out here. You end up having to turn the volume higher on the radio to hear it. Maybe it's noisy and all that. So a weak local oscillator can make the radio weak. A missing local oscillator, you can't tune the radio. I don't think that's the case here. I don't think it's missing. Could it be weak? Yeah, it could be weak on the bands that we're curious about. Now let's follow the antenna here. Now that you got an idea what the local oscillator is doing, we'll just follow the antenna. So of course radio signals are affecting the antenna, and that effect is being pushed down this wire, in this case through this coil. And then where? And then to ground. The way they've shown it, this switch with this ring is actually grounding out all the other coils. Just shut them off, get them out of the way. This is the only one that's energized by the signal on the antenna. Okay, so the signal here is transformed into this side. We have a trimmer capacitor to compensate for variations in the manufacture of these coils. Installation of them too. These are some of the trimmers that I've been adjusting in the radio, you've watched me do. The output then finds its way to here, where it meets up with a big tuning capacitor. So there's a resonant circuit between this coil, yes, and this one too, believe it or not. They're all kind of tied in there. And that is fed right down to the grid of this tube. So now we know this tube is doing nothing but amplifying the signals on the antenna, but not everything on the antenna. The antenna is partially tuned already. So what's arriving at this grid is a range of frequencies around the one that we're targeting, the one we're trying to tune in, the station we're trying to tune in. If these are really sharp, then all that's left here is pretty much the signal we're trying to tune in, if these are really sharp. Okay, so what's the tube takes the signal from here. This is a very delicate thing here. It's basically a piece of wire hanging around your house, your backyard, or wherever it might be, just sticking out there in space. If you can easily drag this circuit down by hooking too much impedance to it, not enough impedance to it, let's put it that way. So in a sense, this very delicate, weak deal here, there's not a lot of push from the antenna. All it's got to do is operate this grid, which is easy to do because look, it's pretty much just a piece of wire, right? Pretty much. So this guy is going. What comes out of here now is much stronger. You can do more with it. And what do they do with it? So they fire it through another set of tuning coils. So tuned here, tuned here, tuned at the RF frequency, the actual radio frequency. Trimmers again, secondary side, same sort of thing, right? And the output is fed, and we looked at this already, down here very carefully to this grid in the mixer tube. We need to know what's getting to this grid. I think that's the first thing we need to know, is what is making it to this grid. Now I can hook a lead right on this terminal here. For instance, what I'm thinking of is using my oscilloscope. Well, the oscilloscope has a 10 megohm input impedance. I think it's 6 or 7 picofarads or something, and then I have the lead on top of it, another 6 or 7 picofarads. Fiddling around in these weak's not quite the right word. Sensitive maybe is the right word. Sensitive circuits here, high impedance circuits. Popping on equipment and that disturbs them. Can knock the signal out, can change the tuning, and it happens instantaneously when you connect your equipment. So you can't necessarily know that your equipment is what you actually end up testing. You're testing more your setup than you're testing the stuff. So I want the stuff being this stuff. So I want to hook up my oscilloscope in a place where it will not disturb any of these coils or any of this. And the safest place to go is on the far side of this tube, right on the entrance to the IF. What should be there is everything. Should be 4 signals there. Okay, so again, take this with a grain of salt. Maybe not all 4 are there. Another place we could go is right on this grid. Now what happens if I hook up a 10 megohm essentially resistor to this? Look, right on the capacitor here, right on the coil. they don't really show clearly how the other side of the coil is being handled here. They got a shorting bar showing here, shorting out this one. They don't actually show where this goes on this schematic. Huh. This is an oddball switch too. This is an odd thing. On the other schematic, it's shown more pictorially to wake you up to the idea that there's something odd going on here. 1, 2, 3, 4, 5, 6, 7, 8 positions, but only 4 snaps in the switch. So it's got to be jumping 2 every time. So it could be there's more shorting bars here that aren't shown or something. 1 snap and this switch will jump over to here. And these shorting bars will show up here. And I just bet there's more coming along behind. Maybe not, I don't know. So these switches are jumping 2 posts at a time when you snap them. Okay. What now? It's kind of interesting that this part of the switch is shown with this grounding scheme here, grounding out all these other coils, but on the secondary side they don't seem to be quite as worried. Maybe that all makes perfect sense. Well, I'm sure it does. Now, what's going on with this tube? So this tube, if you look at the cathode, comes down through 2 resistors and meets ground. On this schematic, by the way, they don't use dots to indicate connections. Anywhere wires touch, they are connected. If they're not connected, they hop. They use the hop technique on this schematic. The other schematic's different. So that's a connection. Come down here, and then it has the switch, which can... What is this doing? So in position 1, position 2, it's not doing anything. When you get to position 3, the 1270 ohm resistor combination becomes just a 270 ohm. That's a dramatic change. That's a big drop in resistance. It's a big drop in bias. We're reducing the bias, the negative voltage between the grid and the cathode when you switch from long wave, broadcast band, shortwave, and super shortwave. So in the short wave, they change the bias. Now that's happening in another tube here too, isn't it? Isn't there another tube that's got the same thing happening to it? Where is it? I can't spot. Here it is. These switches. What are these? These are. What are these doing? This looks very similar here. 470. You know, typically cathode resistors are in the hundreds of ohms type range. We go up. There's the 270. It's the same arrangement, isn't it? It's just pictorially done a little different. Maybe we'll put this 270 down here. It might have been just a little bit clearer. Huh. There's exactly the same thing happening here. And this is a 6K7, and this is a 6K7. I'm not doing anything funny with this one. And I'm not doing anything with this one. Well, I just have no knowledge around the benefits of doing this, you know, related to the frequency of operation of the circuit. You know, I don't know how varying the bias here is somehow is band sensitive, is made band sensitive. I don't know why. So this could be part of the picture of the problem. Could it be? So I think the radio is working good on broadcast, good on the lower shortwave, but bad on the high and bad on the long wave. And you know, I may have got this confused in my head too. I mean, when we do these tests, it'll sort this out a little better. That doesn't seem to add up with the switch being the problem and biasing being the problem. It'd be a fairly easy thing to find out if this is working properly, I think. What other fancy tricks are in here? quiet here while I look for fancy tricks. Don't really see any. Now all the larger capacitors have been changed in here, like this 0.1. These are all changed, but the smaller ones, 50 picofarad, these have not been changed, on the basis that the chance of them being bad is low. There still is a chance. Now let's think about this. AM gets through, seems to get through, the broadcast band seems to get through. What is it that happens that would change dramatically the circuit path? So a different band is going through a different component. I don't see anything like that. It seems to me every band, except for these individual coils themselves. Could there be problems with the individual coils? Well, it's not very likely. It's not very likely. I mean, it's possible. So, for instance, corrosion or something may have opened a lead on this. Something like that may have happened that would deaden it. Well, when we do testing, we'll start finding this stuff out. If I find that, certain bands that can't get signals through, I'll just keep working my way back until I find the signal. And then I know I will have crossed the dead spot. Okay, I think I've stared at this enough. Let's try something. I can always come back to the schematic later. Okay, so what I'll do is stop for a little bit, get the radio operating, get everything set up, get all the equipment operating the way I want it to operate, so we're ready to make that first measurement. We'll start on the AM band where we believe the radio is behaving or performing normally, so we believe, and that'll give us some sense of normalcy in the test I'm doing, and then we'll compare to the other bands and see if signals are getting through or not. Okay, so just turn off the sound from the radio here. So I think what I'm going to do as a first shot at this is go through each band and perform exactly the same test, where I'm going to basically ask how much input does this radio need to get that much output. So what we're looking at right now is the AM band. We'll turn it back up here. So we're listening on the AM band. Sorry about the hum, just ignore the hum. And the tone is what we're interested in. The output of the radio is this level right now. Conceivably, knowing the input level, we should get, I think, well, I don't know if it really should be exactly the same, but it should be similar on each band, I would think. Maybe not. Maybe the radio's sensitivity by design varies from band to band. So anyway, let's just go through this, guys. I think the difference is dramatic. We shouldn't have a dramatic difference. Right now, I've calibrated this. So we have 100 times 10 microvolts going in. I've got a little chart here I'm going to plot this stuff on, or write it down at least. So coming out of the signal generator is 100 times 10 is 1,000 microvolts, 1 millivolt. So I'm going to write here is 1,000 microvolts. We'll try to get this to the same. Well, we'll find out. This is the one we want to get to the same. So this guy is reading basically 1.4 right now. 1.4. So it's actually 0.14 volts in reality. And that's being measured across the volume control, not at the speaker. So basically at the output of the IF is the way to look at it. And then the input of the IF is on my oscilloscope. Got a camera on. So now this is hooked up to the grid cap of the 6A8 tube. So it's essentially the output of the very first RF amplifier, the 6K7. So we're kind of looking at the signal on the antenna as amplified by the first tube and presented to the grid of the mixer tube. Signal grid of the mixer tube. So it's going through two sets of coils to get there. Two tuned circuits to get there. And what is it? So we see it's 0.5 volts per division. That's roughly one division. It's roughly half a volt. I'm going to call that half a volt. Half a volt on the grid of the mixer. Now, how do we know all this is real? I'm going to tune the radio. Maybe it's not even peaked up, in fact. I'm going to tune the radio and we should see everything go up and down. Let's just keep an eye on the scope for a sec. How do you like that? Well, okay, there's proof right there. What am I doing? Everything else is going up and down properly. So my test here is bogus, or what am I actually getting on the scope there? I shouldn't really be anything there. I've got the scope ground lead on. It's right on the cap of the 6A8. Now let me change bands. So that's the lower shortwave band. That's the broadcast band. That's the long wave band. What's there? Why is there something there? Maybe that's just the output of the signal generator. That's okay. Let me change the output of the signal generator. Nothing. Okay, this is getting stranger. There appears to be a signal there where there shouldn't be one. Okay, just concentrating on the signal here. The picture maybe a little bit better. Now, there's some camera effects when you're looking at a screen like this, so I'm going to speed up the sweep here. Well, it's pretty high frequency, whatever it is. It's off the charts, so to speak, on my scope. Huh. Really? I haven't got a factor at 10 switch here. Flip, do I know? Well, wow. Huh. I don't know what to make of that. Let me disconnect the scope lead completely from the grid and see what happens here. Goes away. Back on. My gosh. What is that? Signal generator. Let me just kill the output here completely. It's way down. Nothing happened. And tuning the radio doesn't... Oh my gosh, look at that. Can you see it getting bigger? You can't see what I'm doing. Oh, what just happened there? I'm tuning the radio, tuning it back now. What's happening here? What is that? I'm just tuning. Sorry, you can't see my hand. Just tuning in one direction. The only thing I can guess is there's a whopper oscillation in this radio on its own. Okay, so I'm reaching the end of the run here, I think, on the capacitor. No, there's more to go. So there, I've hit the limit now of the capacitor is completely open. Okay, this is a totally unexpected result. Is it because of the test I'm doing? I've hooked up my scope and my scope is creating this. I don't think so. Is it, what the heck is it? What the heck is it? Let me speed up the sweep again here. See, my scope doesn't trigger. Let me turn this up. My scope doesn't trigger very well. Start using my other scope here, I think. Yeah, I'm not going to get this to trigger at all. Yeah, so we really can't get a good look at the wave shape, but you know, that suggests the frequency is beyond the range of the scope. That's what that's suggesting. And I think this is I don't even know what the limit of my own scope is here. 50 megahertz maybe. I don't see it written on it anywhere. Okay. Well, Okay, an observation, I don't know what it means. Let's just keep going through the bands here. I'm going to slow down the sweep again so I get a little bit of a better look at that. And this voltage is, you know, I'm on the 0.5 volt per, you know, there's over 2 volts there. Holy smokes. Okay, different bands. That's long wave. That's AM, or broadcast. Oh, wait a minute, I got this all wrong. I got this all wrong here. This band switch keeps fooling me. So I think that was the higher one. This is the medium shortwave. This would be the AM band here. And this would be long wave. What's happening? Every one of them is showing something. I'm turning off my signal generator's turned right off. So there's no way the signal generator is producing anything that would do this. What I'm expecting to see here what's happening? What is happening? Oh my gosh. Let me get a different view here. That was nothing. Okay. Oh my gosh. Okay, let's disconnect from the antenna. Didn't do a darn thing. Let's pull the ground off here. Knock the hum down a little bit. So at this point, the radio is now connected to this meter, that scope. That's it. The scope and the meter are connected in very different places. This is at the output of the IF. A little more visible there. Output of the IF and grid of the mixer tube with the antenna signal on it. There's no antenna connected anymore. What if I short the antenna? Let's do that. Why would you do that? I don't know what else to do. Let's try that. Oh, son of a gun. A little bit of frustration. There. Jeepers creepers. Okay, everybody focus now. Shorting the antenna. And do a thing. This is now the antenna on the radio. Is it, am I seeing the oscillator? Is it the oscillator that's doing that? Well, if it's the local oscillator and we happen to be seeing it, I guess that's quite possible. So we'll go on the AM band here. You can hear it. It's a little bit reassuring. Now, the local oscillator, I think we're tuned around. I'm going to turn on the signal generator again here, which is not connected anyway. We're tuned around 1200, I think. It sure sounds normal. I could pull some tubes out at some point. You know, we're on the AM band here. I can signal trace. Actually, I can signal trace the long wave and the AM band with my signal tracer. But this frequency here is not going to do anything. You're not going to hear that. Oh my gosh. So we're seeing that on the grid. What are we seeing on the output of that same tube? Am I for sure on the grid of the right tube? I'm sure I am. Well, the problem is the out, like that tube is way up in here. I could make contact with the, I could stick a probe up there, it's possible. Oh my gosh. Oh my gosh. Okay, so 6A8 plate. 6A8 plate. Schematic 6A8 plate is 3. Well, look at 3. 3 has a couple hundred volts on it. Look at 3 with the scope. 3 with the scope. Okay, let's try it. Disconnect the scope and the signal went up. And you might think, well, that's just because the scope is draining a bit out. It could be other kinds of effects going on. For all we know, that signal's gone now. But maybe we'll see it on the plate. And that's the advantage of doing this. So, down to the plate. I can try like this. It's a long ways down there. Plate is 3. I can see it. This clipped on. No. Number 3. That was it. Clicking go then. It's clicking nicely and then it stopped. Scope charging up or something. So there, oh, there it is. I assume that's the same thing. Of course, that signal, when it meets up with the IF, can't get through the 465 kilohertz IF. It's got to be enormously high in comparison. Whatever that is. So is that coming out of the 6K7? Okay, we can take a look at the plate of the 6K7 and see what's coming out of it. The 6K7 plate is also the 6K, it's a say, mistake here. Pin 3. I guess they like pin 3 for plates. Pin 3 is the plate, 220 volts on it. That would be this tube. And can we get at it? Can we get out there? Appears to be right in the clear. What's coming out now? Huh? What are you gonna do about that? So the only input is this piece of wire here. Get rid of that. Now there's nothing. Nothing at all. Let's go look at that again. Pin 3. Oh, watch your fingers, man. See, there's something there. So does that make it to the grid of the 6A8? The grid is the grid cap, and we did look at it. Why did it look bigger on the grid cap? Why did it look bigger? Did it look bigger on the grid cap? Oh, it's just a hassle here. Okay, camera's getting in the way a bit. Grid cap of the 6A8. You know what? I had clipped onto this frame. Isn't that all grounded back anyway? Oh, let's click here. Yeah, it's all the same. Okay, ground's on. Oh my gosh. What's the scope gonna do here? I can barely see that thing. Here we go. Oh, oh. So that's the grid cap of the 6A8 with a great big whopping signal on it. There's the grid cap of the 6K7. So that looks just like nothing. That looks like what you would expect. But out of the 6K7 comes this apparent oscillation. I'm going to stop for a minute and we're going to try to see this oscillation as a radio signal being received by my little SDR radio. We'll see if that provides any insight about this. But what it looks like is the front end is oscillating wildly. It's something that's supposed to prevent oscillation is not preventing it. But the oscillation is so high you're not going to hear it or anything like that. But it's got to cause problems in the radio. Like it could trigger an AVC voltage. No, it can't, because it's high frequency. It can't get through the IF. Just busy up the tubes. Okay. Yeah, let's stop for a bit here and get things set up. Okay, so if this doesn't maximize the confusion level, I don't know what will. They're looking at my SDR radio down there. It's tuned. The red line on the screen is tuned to 152 kilohertz. It's way down there. Not to worry about it. So the objective here is to spot a powerful high frequency signal way up in frequency from here. So we'll go looking for it in a minute. First thing I want to point out is this very strong signal right here. You can see it's higher than anything. We're looking at the grid cap of the 6A8. I'm going to tune the radio. Get my hand on the knob here, and you'll see that move. So I think that's the local oscillator. Oh, yeah. So I'm at the end of the capacitor run. That's as low as it goes. So that's about 850. So you take 450 off of that. 850 leaves you 400. Huh. That means the radio's tuned to 400. 400. Okay, well, maybe this isn't what I think it is. It's kind of funny. It went down. Where to go? It's just fading out. Well, here we are. Land for the SDR. There's something weird coming in from the other side. You know, that might be the. You know what? I think that is the local oscillator coming in. That red thing. So if you're going to try this, you might have the same luck as me with an SDR. If you work with it long enough, you can spot the signals you should be interested in and ignore all the rest. So I'm tuning the radio right down to the bottom here on purpose to find out where that local oscillator comes to a halt. There we are. I've hit the bottom there, and the oscillator stopped at about 9,750, something like that. So you take off 450. From that you get, guess what, about 530. There you are. That's definitely the local oscillator there. That's really not what we're interested in. Now, I haven't been watching the scope here. What's it been doing during that? Let me tune back the other way and watch it. Aha. So, this is just, I'm watching the oscilloscope now. It's the signal, whatever it is, just getting bigger and bigger on it. Okay, so leaving the radio like this, let's see if we can figure out what this frequency is that's in here. Just going to jump the, whoops. We're going to jump the frequency range of the receiver here up. It's at 2 megahertz here. There we go. I'm looking for a large signals one right under the red line there. That's interesting in itself. That's huge. We can listen to these signals through the SDR. Just turn the speaker on. No, I don't know what it is. Who knows? This could easily be something out of the SDR itself. Let's just keep going. Up. Another large signal here, but this is nowhere near the frequency we're looking for. We're looking for something way up high. Something way up high. Let's go way up high. Oh my gosh, I don't think this is going to work out. There's significant signals all over the place. Look at this one. So, so where's this coming from? Let's just keep going. So finish this off. I think this frequency is up way up in the sky. Let's go way up there. 18. Because my scope doesn't seem to be able to see it. It's got to be way up. 30 megahertz. 40 megahertz. This didn't change much. Yes, it did. 30, 40. And this isn't going to work out. Not the way I'm doing it. I can't identify a particular, wild signal in here. Yeah, so that didn't work out. Okay, enough of that experiment. Well, so I have not identified this thing at all. I think it's real. I think there really is an oscillation in this radio. Is it really causing a problem? I don't know. I don't know for sure. It can't go much further than the front door of the IF stages. Maybe what I'll do is I'll study. I think I'll stop at this point for a while. I'm going to study the schematic, see if there isn't some kind of snuffer capacitor that's not snuffing. I don't know. I don't know. I don't know. We're looking at the grid of the 6A8 with the 6K7 in place, the first RF tube. What if I pull that tube out? It's pull the grid cap off of it. I can do that. That's easy. Okay, let's pull the grid cap off it. What will happen? And we are listening to it. You're bound to hear this. Don't think I want to stick my fingers there, not because of a shock, but because it would introduce. This will introduce noise too. Okay. There we go. Coming on. Didn't make any difference on that screen. That's kind of interesting. What about the other bands? Are they still doing this thing? How can all these different bands be doing this? So that's still there. This is broadcast. Shortwave 1. Oh, I'm wrong again. Oh my god. Shortwave 2. Shortwave 1. Broadcast band. Long wave. Ooh. Wow. Just driving me nuts here. You know, it's really a shame the trigger won't operate on this scope properly. And it really makes it difficult to tell what frequency we're looking at. But it's definitely really high. What about just tuning it in on a regular radio? Just a regular radio, and try to tune in what must be emitted from this radio, I would think. So if I can get a coil close enough, well, it should be easy. Well, why do I even care? Let's say I find out it's 52 megahertz. What am I going to do about that? It doesn't lead to a solution, knowing the frequency. What might lead to a solution is studying the schematic. So I'm going to go away and do that. Okay, maybe just to be sure that I'm not being fooled by seeing the local oscillator on my scope. Just to be sure, I'm going to try to ground it out. So what I'm going to do is I'm going to put a clip lead, this one in fact, right on there, and ground it. And that should ground out the local oscillator. And then we'll see what happens on the scope here. Keep an eye on it this way. Easiest way I can do this. Grounding of the local oscillators. Get on the top of the capacitor here. Oh my gosh, what a busy spot this is now. Camera in there and everything. Oh man. I can't even see the top of it. Well. Oh my gosh, wires getting tied up taut here. It's a real tangle. Okay. I need to get a look at that capacitor over there. I'm going to go right on the plates. You know, it only takes a moment to figure this out. It's just a momentary thing. So I can do that. So I'm going to here. And I'm just going to touch the stator plates over here. Think about this for a minute. Just before you do that. Just take another quick peek at the schematic. Am I about to blow myself up here? About to apply a ground right here. No, this is on its way to a grid. Right. So you know how much can be on there? It can't be any. So grounding this, I can't imagine that's going to cause any kind of problem. Is there a bias voltage on here? No. See, the bias is developed in this grid cathode resistor. That's good. Okay, I think we can ground this, no problem. Hey, let's find out. These are things that you know, other repairers, maybe they do these things routinely, and I just haven't done this routinely, so I'm a little hesitant. So grounding right onto the plates here. Boom. Blocking. There we are. done. It's coming out of the oscillator. You know, that might not be too surprising. I mean, the oscillator is a circuit designed to oscillate. And it's meant to oscillate at a particular frequency, of course. Is there any chance I'm just misreading the frequency entirely? You know, if you have your scope running fast, the sweep running fast, way beyond the frequency you're looking at, you start seeing a straight line on the scope. You don't see that. That is really screaming out a high frequency. Even if my trigger doesn't, scope trigger doesn't trigger right. Like a stupidly high frequency. Ridiculously high frequency. No reason to think it can't be possible. Now, I'm just grasping at straws here. Well, problems with the local oscillator. Let's go back and look at the schematic again. Local oscillator. So there's a feedback to make this oscillate. The feedback's got to come through some kind of amplifying tube. So it's probably got to be this guy. So feedback. What's that? Look right in there. They're showing it pictorially different than the other grids. Why would that be? The draftsman couldn't fit it in unless he dotted the line. Something coming in on the ABC. How about that? It could be an oscillation generated way up here, fed back through the ABC line. So it looks like it's coming from here, but in fact it's getting fed back through the ABC line from out here somewhere. Well, I would find it out here. Pretty far-fetched to think this stuff can oscillate at such a high frequency. A little far-fetched out here too. What could possibly be wrong? That would make the... Let's assume the oscillator is oscillating with two frequencies. The one that's intended and this other wild thing. A very high frequency would be snuffed out with a capacitor going to ground, like this. See, this guy's not in the circuit. It's got to be in the circuit all the time. That's interesting there. This is a straight transformer. This is an auto transformer, another auto transformer, and then down here is a straight transformer but tied together at the bottom. 3,760 picofarads. Who puts capacitors in with this kind of precision? 3,000? What? Really? That kind of precision? Really? What one was that? C16. C16. 0.00365. Well, it's a curious number, 365. Not only is that the number of days in a year, that's typically the capacitance of the big tuning capacitors. I think. 00365. What's happening with this one? C17, just says coupler condenser. And no value. That's kind of odd. We won't worry about that. C16. 0.00365. Just nobody's got capacitors with this kind of precision. But on this schematic. There we go. What's that weird value? This is 1100. This is 430. All the oscillator coils have two adjustments. 1, 2, 1, 2, 1, 2, 1, 2. Yeah. Sometimes when I'm really at a loss, I just start checking things that I believe to be true to see if they are, in case they are. So just another form of shooting in the dark. Wow, 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 wow. Well, you know, it's pretty dramatic. Pull this tube right out at this point and see what happens. Okay, let's do that. Let's do that. Some might see this as an act of desperation. I think so. So I think I'm going to shut the set off to pull this out, and I don't want to burn my fingers on it either. So. Oh, good show. The line disappeared on the scope. That's good. Okay, tube, you're out. What happens now? So, as I sort of alluded to, this problem may not be a problem. It may just be something curious that I'm going overboard on. You know how big that's getting. Isn't that bigger? The scope. That's bigger, isn't it? Bigger's not necessarily better. I keep thinking that there's just something here that I'm really something I'm really messing up on. Wow, look at that thing. Tune the radio again. It's getting bigger. Tune the other way, it gets smaller. At the end of the road, bigger, 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 bigger. So changing the tuning capacitor changes this oscillation. I am totally stuck. Okay, let me stop for a bit. So maybe fortuitously, I just happened to look at the SDR, and at 70 megahertz, there's something interesting happening. So let's take a look at that. So the red line here is right on top of this white line. This white signal all by itself out here. Now what I'm going to do is I'm going to turn off the radio and watch what happens to this signal. Put on my headphones. What are you listening to? Okay, perfect. Okay, power off. Okay, power back on. I'm watching the scope here. There it is. So as soon as it shows on the scope, it shows here. Is this the frequency that we're seeing? Is there more of these? If you notice, I'll put the red line right on it. See, it says 77 over. This is one of the strongest signals I've ever fed into the front of my SDR. Let's go see if there's anything else like it. 2. 2. There's something right there. Okay, I'm gonna turn off the radio and see what happens with that. Huh. Turn the radio back on. Okay, so again, using the SDR to do this, yikes. Getting another radio in here that I can tune 70 megahertz, tune up in these frequencies. Don't I have a radio like that? I do. So I'm gonna get another radio in here. I'm gonna fool around. I'm gonna bring in my patrolman radio. Okay, a great chance to use this great patrolman radio. Had one of these when I was younger, and it just went on its way, and I managed to grab this one at a yard sale. So it's fantastic. Let's get it going. So I've already looked. It doesn't actually have 70 megahertz on here anywhere. This band stops at 50. This one starts at 88. So I don't know what we're going to get. And what band are we on? So right now we are on shortwave broadcast band number 2. This is regular AM radio. Okay, we're just going to go through all the bands here. Next band up. This is from 2 to 6 megahertz. Oops, did I bump something there? This radio may have its own problems. Shortwave band 3, 6 megahertz to 18. 18 to 6. There's something. Something there. A couple things, I can retune this radio and see if it does anything. We could pick up a local oscillator on here easily, but the band, I don't know what band I'm on. Let's try this. Tune the big radio now. Pitch around here without knocking everything down. Okay, didn't do a thing. Something very strong here. That's it. So there's something coming out of the big radio at about 12 and a half megahertz. I'll convince you by turning the radio off on this one. That's a really strong thing. Just turn off the radio, Jeff. Away it goes. Okay, so I don't think there's any question now. There are wild oscillations going on in this radio. Let's keep going. Let's keep going. How do you work this radio? FM broadcast band, we'll skip that. Public service band number 1. The frequency is 174 here. 174 down to 144. Okay, I'm going to kill the power briefly. No, not from the radio. I don't think that's from the radio. Okay, we'll just keep going. We're fine. Public service band number 2. Looks like 30 to 50. Needs a cleanup. Ah, that's the radio. It's pretty high frequency. It's a little crazy. Now we're way up. This is crazy. 460 megahertz up to 500. If we hear this radio up here, oh my gosh. Ah. Dirty band switch. Let's try again. Nope, I don't think that's the radio. Nope. Aircraft control band. So this is basically right in the middle of the FM band. Wow, it's just too quiet, isn't it? What's all that? Nope. Who knows? Nope. Okay. So it looks like. Sorry about that. This radio needs a trip in the shop here too. Where'd it go? Where'd it go? There it is. So on this radio, that is 13 megahertz. Oops. It's definitely the radio doing that. 13 megahertz. And maybe more. Maybe a couple of spots. Well, I can't say I've ever really explored this to this degree with any radio. Maybe this happens with a lot of radios. They are issuing spurious signals, even under proper operating. I kind of doubt it, but normally there are steps taken to stop these kinds of oscillations. Wow, I gotta go away and think about all this. This is just really filled my head with so much gobbledygook here. There's that screen. The screen of light. So maybe I'll end up this video with just a few words about a session like this, which happens from time to time, where you're searching for a problem, you're finding things that don't add up, that don't make sense, that you don't expect, that you can't explain. That's loaded with a heavy dose of self-doubt and questions around the test approach and the effective test instruments and everything like that. Now, I ended today's session pretty sure that this radio is oscillating, but pretty sure is about as far as I can get from this experience. I can't be certain about anything. Some of the tests I did, bringing in a radio and looking for spurious emissions, that's not something I do regularly. So I don't know what to make of it all, and I suspect you as a viewer also don't know what to make of it all. Maybe you do. So I'll certainly be reading over the comments on this video because I'm really at a loss as to A, is this real? Is this thing really oscillating at those frequencies? 2, Does it matter? Does it matter at all? Who cares if it's oscillating at those frequencies? And see, what should I do about it? What can I do about it? I got all those things rolling around in my head. So part of what I'm going to do is study the schematic today a little more, and just make sure I understand the front end of this radio. There's nothing particularly special about it, but it seems to oscillate. So that's it. Okay, see you tomorrow on the next video.